som vai sair bem pelas colunas a partir da...
Os oímos perfecto, ¿eh?
Estão a entender o que é que vai acontecer. Nós aqui vamos projetar, vai projetar a voz, vocês também, para aqui, porque está a haver um problema que não está a amplificar. Não sei se é falha de bateria, ontem funcionou bem, hoje não está a funcionar. Lamento. Pois, então onde é que eu vou buscar agora? Não me deram excelentes. Ok, pronto.
So good morning. It's a pleasure for me to announce the next speaker. Next speaker, Professor King Ho, is an associate professor at the National Institute of Education of the Technology University of Singapore. He specializes in mathematics, theoretical computer science, and mathematics education, with a research focus on domain theory, computational thinking, and technology-enhanced learning. A passionate advocate for inquiry-based pedagogy, he has led numerous projects on integrating GeoGebra and coding into mathematics classrooms. He serves nowadays as the current president of the Association of Mathematics Educators in Singapore, and is a long-standing contributor to the International Mathematics Education Common. So it's a pleasure for me to announce all. Please, I think he is online already.
Yes, I'm all ready.
Okay, good morning.
Good morning.
Welcome.
So I think I can start.
Yes.
Right. Thank you for your generous introduction. I'm Weng Ho, and I'm from Singapore. And I take pleasure to give my talk today titled GeoGebra and the Out-Triangle Centroid Theorem. Now, this is actually a case study involving a student's mathematical discovery by exploiting the affordances of dynamic geometry through GeoGebra. So I just hope that everyone of us can indulge a little bit on the geometry as we all do. And without further ado, let me go through the overview of today's talk. The first thing I would do is to introduce the background of the talk and also to motivate some definitions. After that, we will look at how the power of GeoGebra is involved in mathematical discovery, not just as a tool, but we also want to focus on the pedagogical nuances when the human being interact with this software. I would then present the problem, of course, and also the analytic solution that was first proposed by the student. And we will talk about this innate dissatisfaction that we have for the analytic solution, which then bears us down the road of investigating and looking for a geometric solution. And this is where GeoGebra will help us with some of this work. And then I will draw some conclusion from this journey. Let us start without much ado. I will talk about the background of this work. So there is a student who came to me, and she is only aged about maybe 17, and she was wondering, whether a previous work of mine is related to some problem in real-world context that she was actually engaged in. Now, because of her experience in looking at exhibition halls and the setup, so she came up with a scenario that, you have a triangular zone ABC, and that's the exhibition area. But because you need to mount spotlights, they are denoted abstractly by X, Y, and Z, and they kind of forced to be on a triangular equilateral triangle frame. And it encloses the exhibition triangle in such a way that each corner is illuminated from a different side. And the objective in her problem is, of course, to try to find the dimension of the equilateral lighting frame that maximizes the commonly lit triangular region. So here is the picture, which I'm going to share screen on another screen. So sometimes you see my head tilt a little bit weird. That's because I'm on another screen, and you should be able to see our favorite GeoGebra. So allow me to make this a little bit bigger. Okay, so here is the picture. So you have the triangle ABC, and the equilateral triangle is supposed to frame in such a way that each of the vertices of the given triangle rests on one edge of the equilateral triangle. Of course, you can quickly realize that there are more than one of these covering triangles. So the student was wondering, how would I adjust the orientation of this triangle in order that I can have the maximum amount of light up area? So that is a fairly reasonable kind of geometric problem. And of course, you know, like all good student, she was thinking, well, you know, this is looking like a typical calculus problem. And I say, well, you know, hang on, let us now first make some definitions so that we can communicate, you know, intelligibly. So I say, okay, well, in that case, you know, you have an ABC, which was given, that's the region. And then you say that the triangle XYZ is an outscribing triangle, and that's the usual technical term for that kind of triangle. But she said, well, it's a long term, so why not call it an out triangle? I said, okay, doesn't matter. But the requirement is that if you're an out triangle of triangle ABC, you better be equilateral by your own constraints, and that each vertex of ABC lies exactly on one side of the outscribing triangle. The other requirement is that, you know, you would wish that the original triangle is being covered by the larger triangle. So that's a setup. Then, of course, after some playing with GeoGebra, she realized that actually there are other out triangles. Okay, let's not mind the total covering condition. Let's also admit some others, you know, kind of triangles, as you can see on the slide. I say, that's fine. And then she said, okay, well, in that case, it's quite clear, and I agree with her, that there are two methods of doing it. The first one is obvious. It's really to express the area of this triangle as a function of some real variable that you choose and you decide. And perhaps you can just maximize A by looking at the stationary points. So that's a very reasonable thing to do, at least for a high school student. Then, of course, the other way is because this thing is geometrical in nature. It should lend itself very well, you know, by using geometrical methods to do it. Now, of course, GeoGebra is very good at looking up to uncover these kind of invariant relations. I say that's good. So I said, well, this is a perfect, you know, place for me to share with us how the interaction between me and the student actually is a kind of the meeting point of analytical rigor with a kind of visual intuition. So the highlight is that the both methods should ultimately coincide. That's where we are going from. Well, to settle some of these housekeeping matters, for the orientation of the angle, we just use the usual clockwise is negative and the counterclockwise is positive for angle labeling. And we want to look at how GeoGebra can come in as a tool for discovery. And that's the whole point of this. Well, we all know that the dynamical geometry systems like GeoGebra, they allow learners to move beyond static diagrams. So it's not the same as you would have on a textbook, but the objects can be dragged, it can be rotated, it can be redefined, it can be transformed. It provides instant visual feedback to conjectures. And I think the intermediacy of this motion triggers what is now known in mathematics education as noticing. That means to say that the learners actually perceive the invariance, the not changing of something within the change. And I guess in this particular project that the student landed herself in, she leveraged on these affordances of the DGS via GeoGebra and to move from just observing to constructing the proof. And I thought that was really nice because it helps her achieve a genuine research level kind of discovery, well, at least for the students level. So it's quite quick. She presented the analytic solution, and it's very easy. All you need to do is to parameterize theta, the angle, made by one of the edge of the outscribing triangle XZY. So the XZH, make an angle of theta with one of the sides BC. Well, I guess she chose BC because the letter A was labeled there. Well, that's fine. And then it doesn't take too long for her to, meddle around with the sine rule, for example, and could show that the area A is just equals to the root 3 over 3 of the square of, and you have the sum of two components. One is the A sine theta minus pi by 3. Now, of course, you know where the pi by 3 comes from. It comes from the 60-degree equilateral outscribing triangle. And you have the other part, which is the B sine theta minus pi over 3 plus gamma, where in this case, obviously, the gamma came into place because the gamma is one of the angles of this triangle that was initially given. So, gamma is fixed, theta changes, A and B are fixed. So this is, a perfect calculus problem. Well, of course, she was not willing to do too much calculus. So a little bit of the cantrip using trigonometry actually helps. So one of the things to get rid of is, of course, the irredundant theta minus pi by 3, and then you transform it using u. And it's not difficult to rewrite this expression by using the compound angle formula for sine of u plus gamma. Then you could regroup this as a linear combination of sine u and cosine u. And so that could then be written as r the sine of u plus cos, where cos is actually the angle made from the arctangent. So there's a printing error here. It's the arctangent of b sine gamma over a plus b cos gamma. And the r is the square root of a squared plus b squared plus 2ab cos gamma. So that's the thing. Well, of course, with all these r and cos into the relation, it's not difficult to see that if you change the value of u, mind you, the u was theta minus pi by 3, then A could observe a maximum value when the sine of u plus cos is either plus or minus 1. Of course, if you do that solution, you can see that the corresponding value that will make it the maximum is either that your theta is 5 pi by 6 minus cos, or your theta is negative pi by 6 minus cos, but that gives just the same orientation because the difference is exactly a rotation of pi. So that's neat. That's easy. A good student could do that. And a good student continue to produce the maximum area formula in terms of A, B, and C. And also, what is the side of that largest outscribing equilateral triangle? All good, huh? Well, of course, the analytic approach, it gives the answer right away. But the student was not satisfied because it is far from being clear why the value of theta, which was obtained as 5 pi by 6 minus cos, should give you physically, at least not in the geometric sense, why should it give you the maximum A? In this geometric context, is really not clear at all. So the focus of this talk is to bring out what she discovered using GeoGebra, and I thought that is something really worth sharing. So here is the geometrical solution, and as Euclid would have said, the geometry, and more geometry. And so let's look at into the GeoGebra involvement in here. So essentially, what we are doing is that the GeoGebra will transform the manipulation into observation. And what we're going to do is to take one of the vertex, which is Z, and you take that to rotate it. in such a way it will still maintain that the out triangle is there, and then you resize smoothly. So the student began to see that there's some regularity in the variation. Now that is a cornerstone of noticing. And so this visual pattern prompted further conjecture, which I will let you formulate together with me, okay? So in dynamic geometry, conjecturing is the natural outgrowth of sustained noticing and sustained intellectual curiosity. And so the starting point is to use GeoGebra, and we'll increase the angle theta in the counterclockwise sense and observe what happens, okay? You will see some kind of a circular motion. And so I'm going to tell you what's so interesting, in particular, after some experimentation, the position of the centroid T of the out triangle. Now, remind you that the out triangle is an equilateral triangle, and in some way, the centroid T determines its orientation and its position relative to the triangle ABC, of course. So allow me to show you what happens when we trace out the motion of the centroid, as I share the second screen. So let me create more space for us to view what's going on over here. So I put a color chalk at the centroid of this triangle. And what I'm going to do is I'm going to rotate this guy. Wow. Let me make it bigger. Huh? Let me try again. Huh? There's this faint little pencil dots there, which is a chalk mark made by the locus of this moving centroid. And that to her was remarkable. Of course, you can see that it's going around in a circle, but which thing is going out in circles? So she thought, wow, that was very nice, right? And she said that, well, could it be that as the centroid goes around the circle, somehow some kind of measurement will determine the size of the triangle? So that's the question that she had in mind. So looking at the picture, connecting with her intellectual curiosity leads her to that question. Huh? So she observed, like the Earth goes around the sun, and she observed that the centroid goes around something that she doesn't know where the center is, she doesn't know where the radius is, and she doesn't know why should it be that it is a circle. How come? So that's what we're going to do. So in order to see this thing, we have got to make the medians of this triangle very explicit. And as I said that before, it is all about obsessive attention to the dynamic experimentation. That's where you notice. But what do I want to say this? Because notice means something catches your eye. Sometimes you're not looking out for something, but then suddenly something flew inside, and then you say, what is that? The second type of noticing is sometimes is that we are trying to ask why. And we want to go and look hard at the picture and look very hard at it and look very hard for a long time. And so then suddenly it dawns on you that there is something there and you will see it. So there are actually two layers of noticing. Now, the technological affordance of GeoGebra enables us to, take real-time measurement of dynamic quantities, which is good, and in this case, is the area. There is a visual persistence because we use trace functions and we use the locus tools. Then I can iteratively refine the hypothesis by making advantage of this intermediate feedback. So what we're going to do is going to mark out, the respective perpendicular bisectors of the line segments that forms the original triangle. And those perpendicular bisectors will have to pass through the respective midpoints of the edges AC, that's W, CB, that's U, and BA, that's V. I'm going to show you the picture in a moment. And then we will introduce something which the student thought was important in characterizing the circle. We call them the pivot points of the triangle ABC. And so let's see, what are pivot points? I never heard of this kind of things, but, that's a reasonable thing, I believe somehow. So there was this extreme position. You can rotate the triangle, the out triangle, in such a way that X, one of the vertex of the out triangle, lands up exactly at A, and in particular, XZ is going to be parallel to AC. So it's lined up to be aligned with one of the edge of the given triangle. Then I will take the perpendicular bisector of AC, which is the edge that is being parallel to this out triangle. And I take that perpendicular bisector, I will intersect the median that starts from X right through to M3, which is the midpoint of YZ. So I'm going to do the dynamic version of this and let you see a few possibilities. I'm going to give you a shot at this and see whether you see what I see. Okay, this picture looks complicated, but do not fear, because what we're going to do is that we will going to, move some points. I'm going to do this. I'm going to move this triangle, and I will move it in such a way that the position of the A and this will align. Can you see that? So that's the one that's given on the slide. That's the alignment. And you will see that the red line over here, which is the perpendicular bisector AC, intersects the median, which passes through X. And so that forms the point L. Okay? Now, of course, you can take turns. It's not fair to be just on AC. Why not we do it on the other edges? For example, on BC, as you can see. Then you will create another guy, which is called N, which is again the perpendicular bisector of the side intersecting the median. And then you can also do it on this side, for example, on here. So I'm going to change the orientation in this way and do it onto here. So now it's sticking along the edge of AB. And then you have a point M over here. So you locate 3 points which are critical. And because of the way the lines are pivoting around those fixed points. So I thought that was a nice thing that the student issued the meaning of pivot, to this point. So it's very natural to do that. Let's come back to the slide. So we have all the 3 points, L, M, and N, which are critical to the analysis. So she say that these are the pivot points. And why should she want to believe that pivot points are actually good? Well, if you take a second look at the picture, you could easily see that the pivot points are points that actually lie on the circular locus of the centroid of the moving out triangle. So that she saw something there, which doesn't change. Your out triangle can rotate all it cares, but it doesn't change. That guy doesn't change. Those 3 guys don't change. So these pivot points are good points. And then she said, I keep rotating. I keep finding that these intersections of the perpendicular bisector of each edge with the corresponding median always pass through each of the pivot points. There must be some invariant there. Why? Why is that correct? And so, if this is the starting point, she was so curious why this is true. So, I think in that case, after some experimentation and some looking very hard, and this is the part of the picture that I just want you to focus on. For the moment, my friends, do not look at the red circle. I just want you to look at the triangle ABC, and there is this very special out triangle, which is A, Y, 1, and Z. That's a special position, you remember? And this is exactly the place where I created L. I just take the perpendicular bisector, which is the blue line, and I'm going to intersect the median that starts from A. So that's the point L, okay? Now, of course, in this case, it's quite clear that AY1 is just parallel to AC because it is a special one of which we cause the alignment. Now, the next thing you want to do is to say, okay, fine. I'm going to take an arbitrary out triangle, and that's just XYZ. I'm going to take the point X and the point L, and I'm going to pass a line through it. So I'm going to pass a line through this guy. And it's going to hit somewhere on this side of the ZY. Now, of course, I'm not knowing that it's going to hit the median. I'm not going to know that it hit the midpoint. Because if I know that it's going to hit the midpoint, then that's exactly what I want to show. So I labeled that angle CXL to be equals to delta. And my evil plan is really to show that delta is 30. Now, I'm going to tell you why this is the case. The reason is because in order to show that XL and M3, which is the median of this arbitrary out triangle, actually still passes through L, is equivalent to actually showing that the XL extended should hit the other side of the triangle ZY at 90 degrees. Now, of course, that would mean that it is the median, right? But do remember that the angle XZM3 is 60 degrees. It's because it's an equilateral triangle. So therefore, it follows that in order to show that that's 90, it's just the same as showing that the other complement, which is angle CXL, is precisely delta being 30 degrees. So it's just good to show that. Well, to do that, the student is inspired by the fact that it looks as if there is a circle passing through the points X, A, L, and C. But why should it be? Well, the answer is quite clear. Because she said that the blue line bisects, this is a perpendicular bisector. It bisects AC. And so then you form an isosceles triangle ALC, which has got two base angles, which are 30 degrees. That means to say that ALC itself must be 120 degrees. That's easy. That's simple angle sum in the triangle. And next, she discovered that because ZXY in particular was 60 degrees, and 60 degrees add up to 120 degrees, are forming the angles in the opposite segment, which means that if they add up to 180, which they do, that would make the point XALC exactly lying on a circle. It's cyclic. Wow. And then you fill in the red circle, which is the unique circle passing through these 4 points. And then next, she then reasoned that because CL is subtending the angle ACL and also CXL, so delta has to be equals to 30 degrees. What an eye-opener. I mean, you can't help but see that there is this happiness that cannot be contained in her. So this is so nice. It's a major discovery of her life. So this delta is 30 degrees. And so what does it say? It says that we have finished the proof, because that means to say that 30 with 60 gives 90, and it has to be that XL passes through the foot of perpendicular. So that's the median. Such a nice theorem. So she moved on. You know, I know now that I have got all these, pivotal points, and no matter how you're going to rotate, those corresponding perpendicular bisectors and the medians always pass through these pivot points. Now, why is it that the locus is going to give a circle? It's still a question that is not answered. So that means to say that we need to pursue further. And so this picture is the general situation. You have got the pivoted points. But how does it explain that this is going to be a circle? Well, if you now focus on the centroid T of an arbitrary out triangle, you will of course see that T is the intersection of the median of the out triangle. So that means to say that if you were to look at L, T, and N, this L and N has to be resting on the respective medians. This is the trick. And so LTN is 60 if you are looking on this side. But of course, when T flips on the other side, then the angle is 120, not surprising. So that means to say that no matter how you're going to rotate, this angle that's subtended by the chord LN is to be 60. That tells you that T has to move along an arc of a circle, the major arc that passes through LN. Well, of course, the minor one as well on the other side. So that shows it has to be a circle. This is so marvelous. So by the converse of the angle in the same segment, it deduces that you must have a circle that goes through all the pivot points. QED, quite nice. Oh, so I say, okay, fine. You have the pivotal points, and I say that therefore, corresponding to a triangle ABC, you have a unique circle that passes through all these pivot points. I call that a pivot circle. And the pivot circle must therefore have something to do with the area of the outscribing triangle. A little tiny look doesn't hurt. It's quite easy to see that the pivot points are distributed evenly around the pivoted circle. And that would be, of course, an equilateral triangle. Now, this is easy to see, because what you have is that the variable point T will take their turn to visit the L, visit M, and visit N as it goes around the circle. So if you look at the GeoGebra applet, you should be able to see on this screen that it is visiting each of its friends. So T goes around to visit this guy, which is L, and then goes around visiting M, and goes around visiting N. And you could see at each of these positions that the angle so made by L, M, and that point is 60, right? So every one of them is 60. So this is so interesting. So of course, this is natural, not something that is far-fetched. And the student quickly realized that it has to be evenly distributed around the pivoted circle. And here's an exercise for all of us and for diligent students, is to show that the center of this pivoted circle of the triangle is actually the same point as the centroid of the original triangle. Okay, this will take some effort, but I'm sure if you actually use GeoGebra diligently and look at the picture carefully, you will see it, okay? So I'm going to leave it as a little riddle. You should enjoy yourself, or we should have some time to indulge on some geometry. Now, before moving on and to disclose our full discovery, it is instrumental to remind us a definition which is classic in geometry, and it's called Fermat point, and this, of course, named after Pierre de Fermat, the French mathematician. And the Fermat point has got several characterizations, one of which is that this point F, is such that the angle AFC is equals to CFB is equals to BFA is 120 degrees. But of course, we also know that it could be the answer to the Torricelli problem, which is to say, if you take the sum of the lengths AF and then BF and CF, you add that together, and that distance is to be minimum. It is as if you put a pizza shop at F, and you have got the suppliers of the different product of the different ingredients of the pizza at A, B, and C, and you say that I want to put my pizza shop at the place so that the total distance away from these suppliers is minimized, right? So there's a famous problem. Of course, you would remember that the standard solution for that, given by Fermat, was to erect 3 respective equilateral triangles and to take the opposite vertices of the equilateral triangle facing the original vertex of the triangle and join them up. It turns out that these 3 lines, which are HB, AI and CJ, they are concurrent and they intersect at F, the Fermat point, and makes it such that the angle AFC is 120, BFC is also 120, and so would AFB. All right, so we are all familiar with that. Now, why do I want to introduce a Fermat point? This is surprising. And it is good exercise to at least, understand this part, that the Fermat point F of the triangle ABC actually is a point that lies on its pivot circle. It's not at all trivial. It's in fact very exciting and pleasing to know that. So what we're going to do is I'm going to take the special out triangle in which XM3, the median, remember, that's a perpendicular bisector of MN, and then M3 is the midpoint of ZY. I'm going to take M and N to be the pivot points of ABC defined and look at it here. Now, this picture is a little bit small. It's a little bit confusing. So I hope that I'm able to reproduce that on GeoGebra on a bigger screen for us to see. But I just want to excite you that this F that you see over here is actually formed by you take an arbitrary point, which is actually this particular point R is the centroid, is now not labeling so perfectly. So you take that, you will be extending a line from H right through that point R and do some geometry. Okay, so I'm going to do that step by step. I hope you could join me in looking at this picture more intently. So I'm going to put it up on the canvas over here. And I'm going to explain the proof a little bit. So just a little bit of indulgence and we are done. And yeah, I'm waiting for GeoGebra to load here. So while that point is loading, let's see whether it's happening. Okay, just hang on there for a moment. Okay. Okay, doesn't matter. It seems that it's not behaving itself a little bit, so it doesn't matter. Let me go back to the slides. Let me try that again. And hopefully we have the picture here. No, we have no luck. Okay, maybe something is wrong. Doesn't matter. So any case, what happens is that if you look at the picture here, it's a bit small. You take the centroid of the out triangle at the position R, and the objective is to use the angle in the same segment again, the same trick, to show that the angle that AFC makes is 120 degrees. So that's the way we can confirm that the point is going to be resting on this particular circle. So we're going to do it backwards. So we're going to take the LR, which is the diameter of the circle gamma. That's the pivotal circle. And then what we do is that we will pass. So we erect an equilateral triangle on this side of the edge of AC. We pass H, a line from H, and join it opposite to B. So all the way hitting B here, and you will hit the point R on the circle. So you will also on your way hit a point on the red circle gamma, which is the pivotal circle, and that point I label as F. So I'm going to show that AFC is 120. Of course, you also need to show that AFB is also 120 and so on. So use the fact that LR is the diameter. So we have the LR over here. So this is LR, which is this particular line over here. It is going to be passing through the center of this. And so by the Thales theorem, you have a subtended angle of 90 by the diameter. The next thing is that HL is a line segment which is along the median of the triangle. So it's aligned with the perpendicular bisector. So it's along with AC. And so you know that the angle so made with that is going to be 30 degrees because it bisects. Then you use the fact that the two angles LXC, which is 30 degrees, and the other one, which is LHC, it happens to be equals to, again, 30. That means to say, again, you use the trick, you can construct a circle that will pass through all the 5 points on the left. So you've got 2 circles. So once you have done that, the next thing you need to do is to start to build fragments of the circle and transfer angles by using angle in the same segment. For instance, your AHL, if you stare carefully at the picture, it is equals to the angle AFL, which also would be 30 degrees. Then you add the 30 degrees to the existing 90 degrees. If you look carefully at this picture, this AFL is 30 and that's a 90. That adds up nicely to 120. Then you sneak around to check out what is the size of AFC. And by the same technique, you discover very quickly that it adds up, that will be 120. So you confirm that this F is indeed going to coincide with the Fermat point. So that's not trivial. At least, I mean, after spending some hours looking at it, it must be hours. Now we reach a point, it's almost near the end of the talk, we'll be able to prove why the outscribing triangle should attain a maximum area at a particular position relative to this Fermat point F. So before that, I'm going to show you a little corollary, a little lemma, not corollary, a little lemma. And to do that, I would hope that this shows up nicely, because otherwise it will be a very big disappointment. So let me try to do that. Again, it is not really showing up. Something is wrong with the GeoGebra here. Anyways, okay, let me try to do that. Okay. Okay. Okay, never mind. It's okay. I think it may be because there is a very bad connection over here. So anyways, what I just want you to imagine is this. I'll show you the picture on another document so you would not be disappointed about the geometry here. So I just want to show you over here the document and you can see what's going on. So if you have 2 circles, all right, with center O1 and O2, and they are known to intersect at 2 distinct points C and F. Now the radii may not be equal, and then what you need to do is you can just pick H, or you can just pick G, doesn't matter. You pick G, which is the point, so H you can just ignore it. And then through G, you draw a straight line passing through F until it hits the other circle at E. Then what happens is that you then join the segment C to E and you measure the ratio of the length CE versus the length GE. So it doesn't matter where G is going to move on the circle on the left. The ratio of CE versus GE happens to be constant, but it is also very interesting to see why this is half. Okay, so again, a little exercise on your part. It's not difficult to see that there's half. So moving on, this is the juicy part of the whole discovery. After playing with the picture, it happens that if you move the centroid right to the position where it is the furthest away from F on the circle, then the area is going to be the largest. So I hope that I'm able to show you the picture of that. So give me a second while I pull up the picture, and I will show you that it will do so. So hopefully over here. So I'm going to show you the picture. There you go. So I'm going to magnify this a little bit. And I'm going to say that if this guy is going to go opposite to this point, which is the Fermat point. There you go. This is the picture. So that's where we are. Okay, you can see the Fermat point clearly at F. And I'm going to do this. I'm going to rotate this. And if the point T is diametrically opposite, can you see this point? Then the area is going to be the largest over here. So after some experimentation, this is exactly where we saw this point. And that interests us a lot. And then it turns out to be the Fermat point. It's so interesting. So going back to the slides, we now detailed the proof a little bit. This is fairly straightforward. It is not difficult to see that at the end of the day, because of the lemma, it turns out that if you want to measure the area of the triangle, it would be, for the out triangle, 3 times the root 3/4 of the length xt squared. But the xt over the ft, as you were reminded, was a constant. And it was exactly equals to half. And so 2 in this case, because it's a reciprocal. And then you know that the ratio of the out triangle is going to vary proportionately with ft squared. So that's why when t goes on the other side of the circle antipodal to f, is the furthest away it could get. And so you'll end up with the corollary that the maximum area of the out triangle for a given triangle is achieved when the centroid T is diametrically opposite to F, which is the Fermat point of the given triangle that rests on the pivot circle. So this is the reason why. But without GeoGebra, this is almost impossible to have seen all these things. Now, the last few minutes, I'm going to lead us into a little bit of a conclusion. So thank you for your patience and, of course, bearing with my, the app not working. But you would have seen that GeoGebra gives the element of play. You have free exploration using the sliders and the dynamic movement. You also give the chance for the student to notice there are patterns, there are invariants emerging from the visual feedback. It encourages the student to conjecture, to form hypotheses. Could it be because of this? And then could you verify it through the observed regularities? Can you confirm your guess? Can you verify them? So the takeaway from this is that technology does not replace reasoning. It doesn't displace it. But what it does in the case of GeoGebra is that it amplifies it and makes the invisible visible. That's the whole point of this. Of course, you may want to say the same problem has already been solved earlier, in fact, by myself and 2 other colleagues from China. And in that paper, we just use a very simple analytic approach. And, my colleague even come up with a method of constructing that maximum out triangle. But we did not notice that it involves the Fermat point. So this case study demonstrates how well-designed GeoGebra environment can transform the student exploration into a very structured kind of mathematical investigation. So earlier methods, earlier discovery, on this topic didn't reveal the role of the Fermat point. But GeoGebra helped us do that. So in this piece of work, we have presented a purely geometrical solution that hinges crucially on the use of GeoGebra. And importantly, we have identified the role that the Fermat point have made in locating the largest out triangle, and all these geometrical phenomenon are being first dynamically observed and then justified analytically. So there is this seamless transition from experimentation to proof, and it mirrors the kind of activities that mathematicians actually do. So in a way, it's very comforting to see and it's very encouraging to see that GeoGebra serves both as a laboratory for discovery, but it gives the student an additional pair of lens for understanding geometry. So with these, here are the references of my earlier work, and also, of course, citing GeoGebra. Thank you for your attention, and I've given some 5 minutes left or so for questions and answers. Thank you so much.
Any questions for someone? Yes, please.
Vou traduzir aqui. So, a person, but
Yes, I can't hear you quite clearly, but if you were to speak nearer, I would be able to hear your question.
hear me now? You hear me now? Repita a questão, por favor. Repita a questão. Repite. No, repítala en español que yo la... Pero repítala en español, por favor. The person in the room asked you, if this kind of results could be stands to use with quadrilaterals?
Okay, very good question. I have done another piece of work some years ago, and it is known as the outscribing rectangle. So you could just imagine if I take an arbitrary quadrilateral and I could ask the same question of having a rectangle that would have the same effect of covering the quadrilateral and also touches each side as one vertex. That is called an outscribing rectangle. Now, I have, with some colleagues, have come up with a solution as well for that analytically. And I also use a technique using dynamic geometry as well. But in that paper, I use another system. But nevertheless, I've also obtained a very beautiful solution. It's been already published some years ago in the proceedings of the Asian Technological Conference in Mathematics. I have done that. And yes, there is a solution for that. And again, we have made use of the some kind of a circular locus to solve the problem. But the solution compared to this one is a lot easier, because this one is harder because you need to identify the pivotal points. But in the other case of the quadrilateral, it turns out that all you need to do is to use Thales' theorem, which is the angle in the semicircle. All right. So that proof is a lot more easier, but this is so much more harder.
Okay. For questions? Yeah.
Sí.
È utile trasladare la idea a 3D, usando GeoGebra 3D.
The speaker in the room asked you, what is your idea about this problem in 3D dimension?
Very good question. Okay, I've also asked the student to do that. But of course, the student find it very hard. So you could imagine, for example, if I have a tetrahedral in the middle instead of a triangle, and I use a equilateral kind of pyramid. It's a right pyramid. So the first thing you need to do is to show that such a outscribing pyramid tetrahedral, regular tetrahedral actually exists. I think it does. And if it does, then I'm not surprised at all by the variation of dimension that the locus of the centroid should be lying on the sphere. I'm not surprised at all if it is like that. Okay, but however, there's too much of a speculation. I have asked the student to consider that, but of course, I think she finds it a little bit difficult. I'm also sure that if we continue to use GeoGebra and there are three-dimensional versions of that, I'm not very sure. I'm not conversant with that. And if there's a 3D version of that, perhaps such a theorem would have a natural extension. So thank you very much for that question. I have asked the student to do that, but of course, it proved to be a little bit too tedious and difficult for her. Thank you.